For the homework, like with 3A and 3B, where we're doing like either the exhaustive or dichotomies, would we just say like the best hand value for
Yeah,
that? Okay, so not like we don't need to go any deeper that like, oh, it could be between, we just say like of the steps we're given, like
Yes.
this was the best
Yeah.
one. Got it. Also, on number 4, we're not given like a like step size to start with, so we just pick one of our.
Yeah.
Okay.
It's probably
Okay, sure.
some little nine conditions. If, coming in the back.
Okay.
Sorry, that's gonna be with just content. From the voices, so I have compressive load applied.
Okay.
So I'm trying to simulate like when you grab a handle and you try to pull it, you apply compressive load on the inside as well as on the outside. Um, and I do that for two cases. Case one, it's a compressor for aluminum 6061. And case two, I change the shear load to be on the side. So what I'm simulating right there, when you push, let's say like a rail car door open this way.
Yeah.
So I just put it on this one. Would I have to also put it like around other parts?
It depends. So, if you, it depends on how you think is best to apply force. So if you're taking it that way, you have a hand that's going to surround the whole handle. Think about it kind of, the force is going to be spread out over wherever your contact is.
Oh,
Part,
okay.
right?
So not just like the side, but the whole thing, the whole way.
Yeah.
But in general, would you say that in terms of compressive force, I am compressing in on this one, so I have my force. Force.
Yeah, makes sense.
As far as like the mesh, I applied mesh refinement to the main area where most of the force is
Good.
going to be there.
Yeah, that's pretty good.
Not so much on the transfer that can be fixed. Full of information and equivalent stresses.
Yeah, looks solid.
Um, for the report, what I need to do, and anything else?
Well, I mean, you have to, it's not just the screenshots. So a lot of it's going to be how you explain it, when you explain the text. These results are good though. I mean, they make sense to me. The mesh looks good. So, it's all about how you kind of explain it in the text.
One thing that I wanted to get down was the yield strength. I wanted to talk about that, such as like how, let's say I change the material to ABS plastic, right? There'll be more deformation in the part. But in terms of yield strength, let's say, it doesn't go over the yield strength. So let's say it's like, oh, this is why I picked this one, or this one, I would recommend this one.
Yeah. Yeah.
Thank you.
So the MATLAB portion, you can just submit it with the PDF as well. So you should be able to turn in multiple files on Canvas. So you just turn in maybe one PDF for your answers and then another PDF for the script. Or if you want, you can put it all in the same. You can combine it all into one PDF as well. Either is okay, as long as I can see the code. Whether it's more convenient to do one file or multiple files, it's up to you. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, hanging in there. It's week 10. I think this is the part of the semester that's one of the hardest to get through because we're right kind of in the middle and everyone's kind of tired. It's fall semester is always such a drag because the only break that we really get is Thanksgiving, and we're still quite a ways away from Thanksgiving. So hang in there. I know it's kind of dragging on, but we'll get to Thanksgiving eventually, and then after Thanksgiving will be Christmas. So we can all look forward to that. Okay, so the plan for today is I'm hoping to finish up our lecture notes on 1D nonlinear programming methods today. So I did want to finish up and show you the code for interpolation methods, and so I know we kind of had that one off last time. So I wanted to make sure I went over that. And then we're going to go over the last method in this section, which is called direct root methods. Okay. Direct root methods, honestly, it's a little bit of a detour. It's not as useful as some of the other nonlinear programming methods, at least for optimization. But the main method that we're going to go over, which is called the Newton-Raphson method, is such a universal method for so many different other things. And so, we're getting so close to it anyway, I would be remiss to not at least go over it a little bit. Just because Newton-Raphson kind of shows up in so many different contexts. When you're implementing your own finite element code, when you're doing, finite difference codes, and so, lots of different numerical methods use Newton-Raphson. So it's we're here already. We might as well go over it just to, just to say that we kind of completed that set. Okay. All right. Another thing I wanted to go over today, and so I know everyone's working on homework 4. So a big part of homework 4 is going to be the MATLAB scripts, right? The MATLAB implementations for problem 3 and problem 4. So I wanted to go over a little bit about, what I recommend that you guys do to kind of tackle those problems. Because if you're starting the scripts from scratch, it can be a little bit intimidating. So I'm going to go over a little bit about how to use kind of the example codes that we have. First of all, how to find the example codes on Canvas. I think that would be at least useful. And then second of all, how I recommend to use them to complete your homeworks. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So before we jump back into MATLAB, let me just kind of do a very, very quick review. All right, so before we left off on last Thursday, we were going over interpolation methods, okay? And so the idea with interpolation methods is, remember, we're working in this unit of nonlinear programming, so we have the limitation where we can't work directly with the objective function. Right? The way that we can interact with the objective function is very limited, okay? And so in particular, with interpolation methods, we kind of limit ourselves to the situation where we can't take derivatives of the objective function. The only thing we can do is evaluate it at certain values of x. Okay? The key word here is evaluate, right? And so since we're limited in terms of how we can use the objective function, the idea with our interpolation methods is, why don't we make a new function that we have full control over, and then we can use that function to take the derivative and find the optimum. Okay? And remember, that new function that we are creating is called our surrogate function. Okay. So the surrogate function, for our purposes, we're choosing to be a quadratic function. A quadratic function is the simplest function that we can come up with that has a very clearly defined minima or maxima, okay? And our method here kind of proceeds in two steps. And so remember we called them phase one and phase two. So I'm not going to go over the full details of these phases. This is just to kind of remind you what they were. So in phase one of the algorithm, we were determined to find the right step size. Okay. Remember what we said was that our surrogate function is only valid up to a certain value, right? So it's impossible really to come up with a quadratic function that closely approximates a function for for all values of x, unless that arbitrary function is a quadratic. And so we kind of limit ourselves so that we only closely approximate it within a certain range. Okay. So phase one is to kind of basically help us compute what that range is. Okay. Right, and then after we compute phase one, phase two is then now that we have the appropriate range where we want to make our surrogate, phase two is to refine our surrogate so that we match the original function as closely as possible. Okay. And if you recall from last Thursday, the process in which we refine our surrogate is to kind of shuffle around the 3 points that we use to choose the surrogate's values. And that's kind of something that we constantly iterate on until our surrogate is as close as possible. Okay. Okay, so that was kind of the method. So at the end of class on Thursday, we did well, not really the end of class, I would say for the majority of class. We worked on an example where we worked this out by hand, so you can kind of see all the calculations being done. And so the next thing I want to show you is the MATLAB implementation. Okay. All right. So before we jump into that, are there any questions on the interpolation method? This is just kind of a recap from last time. Okay. All right. So let me go ahead and share my computer screen here. Okay. All right, so this was the script that we were going over, but actually, first thing I wanted to go over before this is to kind of show you where all the example scripts are. So for basically every algorithm that we're going to be covering in this class, I've already written an example script for you to look at online. And so, the idea with the example script is to kind of give you kind of a starting point. Because for homework 4, and then eventually homework 5, and then eventually for the final project as well, you're going to be responsible for implementing these MATLAB codes or these optimization algorithms yourself, okay? But I didn't leave you high and dry, and so, I'm not telling you to implement these from scratch. Generally what I recommend for you when you're implementing something for the first time is to use the examples as kind of like your base, and then modify the examples according to the problem that you're working, okay? And so let me show you where to find all the example codes. And so if you're on the Canvas site, first of all, I try to post them on the weeks where it's relevant. But if you want to get a repository for all of the example codes, you would go to the Files tab on the Canvas site. And so in here, you'll see that there's a folder for the code examples. Okay. And then here you'll see all of the example codes that I have for the class. Okay. All right, and so the ones that we're focusing on, at least for this first part, are all of the 1D methods, okay? So all of these codes right here. So you can see I have 5 codes here for the 5 methods that we went over. So example 1 here, that is unrestricted search. Unrestricted search is the same thing as exhaustive search. It's just when I wrote these codes, I just called it differently, okay? So you can see here we have a code for dichotomous search. So that was, the second algorithm that we went over. We're going over example 3 right now, which is quadratic interpolation. So we'll go over that. And I have 2 more codes for the other 2 methods we're going to go over today. So the Newton-Raphson method and the quasi-Newton-Raphson method. Okay. So when you're writing your codes for the homeworks, don't start from scratch. Right. Use these example codes and modify them to your needs. Okay. So for the homework problems, you won't be able to just run these example codes and get the result. You're going to have to modify them a bit. And so, knowing how to modify these codes is important, but, at least this will give you a good starting point where most of the method is already kind of implemented for you, and you just have to make some changes in some key areas, okay? So use these example codes. Don't start from scratch, and try to modify them to your needs, okay? That said, once you kind of do a couple of these, then you start to kind of understand how to use the examples. Don't just plug into the example code and then just have that be done. I give these to you so that you kind of look at them yourself and kind of really help understand the algorithm. Okay. I provide these codes just because, I know, MATLAB is kind of a big point of kind of anxiety for a lot of people. And so, I wanted to at least give you a lot of examples to look at in terms of, how these are implemented in practice, or at least how I implement these in practice. But don't just take them and just use them, really kind of, take your time, read through them, and, try to understand the algorithm as best you can. Okay. Because for your final project will not just be a plug and chug. Your final project, you will actually need to, use these examples, but also implement a lot of code yourself. And so if you just do homework 4 and homework 5, or you're just plugging in the objective function, you're going to struggle with the final project. And a lot of people did that last year. So, I don't want the same thing to happen this year for you guys. And so, definitely make sure you're reading the example codes. Okay. I debated for a long time whether I wanted to provide the example codes for you guys this year as well, because last year it was a big crutch, but I did opt to share it with you guys again. But just make sure that you're reading through the code, read through my comments. I try to leave as many comments as I can to kind of explain what's going on, just so that things make sense for them. Okay. All right, and of course, in the class, I'll try to go over the example codes as much as I can, and explain them to you. Just kind of make sure that you're kind of taking notes and ask questions if you're not sure how things are implemented. Okay. Okay, so this is our code for the interpolation method. Okay, so remember, in the interpolation methods proceed in 2 phases. So phase 1, we're going to find the appropriate step size. Phase 2, we're going to refine our surrogate. Okay. Okay, so this is how it works. And so when the code starts, remember, you have to pick an initial step size. And so, even though we're probably going to be modifying this to a certain extent, we have to choose it somehow. Okay. And so for this particular problem, we're choosing to start with a step size of 0.5, but just knowing that, we're probably going to be modifying this as the code goes. All right. Okay, next thing we're going to define here is the convergence tolerance. And so remember, this is something that you need to define in terms of, when to know when the algorithm stops. Okay. So remember, in phase 2, there's a certain point where we check to make sure, or we check to see how accurate our surrogate is. And this was kind of a key parameter for that. Okay. All right, so in phase 1, now that we have our step size defined, we're going to evaluate our objective function at 3 different locations. And so we always evaluate it at x is equal to 0. We evaluate it at x is equal to the step size, and then we evaluate it at x is equal to 2 times the step size. Okay, so those are the 3 x values, x, a, b, and c. And then we evaluate our objective function at those 3 locations, right? And so if you look back on your notes, so this example code here is implement the exact same problem that we did by hand last time. So the objective function is still the same. Okay. Okay, so we're going to evaluate our objective function at the 3 locations. And so remember, our objective function is x cubed, x to the 5th power minus 5x cubed minus 20x plus 5. Okay, so evaluate that at xa, xb, and xc. Okay. By the way, if you're going to be using this example code to implement your own, or you're going to be using it on the homework, this is basically one of the main ways that you're going to modify the code. So you're going to modify the code to change this objective function to match whatever problem that you're working on. Okay. So for this problem, we've set it equal to this polynomial because that's the problem that we're working on. But for the homework problem has a different objective function. So you're going to have to change this part of the code. Basically, anywhere you see the objective function, you're going to modify it accordingly. Okay. So now these next 2 while loops here kind of illustrate the what we're going to do in phase 1. Okay. So this first while loop is to check to see whether we need to make our step size smaller, right? And so remember the criteria for making the step size smaller is if the function evaluation at the midpoint, so FB, if that was greater than our function evaluation at the origin, then we need to make the step size smaller. Okay. So while this is true, right? So remember we went over while loops last time. While loops while loops will repeat everything that's inside the loop body as long as this factor here remains true. Okay. So while this is true, we're going to make the step size halve and then reevaluate our locations and reevaluate our objective function. Okay. But of course, if this quantity here is false already, then we just don't even enter the while loop at all. Okay. So you can think of while loops as simply just like an if statement that you just repeat, and you repeat it until the conditional at the top returns false. Okay. Okay. So even though, we may not even, reduce our step size, we need to include this so that, we have the capability to, even if we don't need to. Okay. Okay. Next thing we're going to check is we're going to check to see if we need to make the step size bigger. Okay. And so the criteria that we use to make the step size bigger is that if FB is less than FA, so if the function evaluation at the midpoint is less than the function evaluation at the origin, and if FC is less than FB. Okay. So these are the criteria that we went over in class, I think maybe not last time, but the time before that. Okay. And then once again, we're going to be recomputing our step size and recomputing our function evaluations here. Okay. All right. So once these two while loops conclude, we're in a position where our step size is perfect. Okay. And likely what's going to happen is that, we're probably only going to evaluate, or we're only going to execute one of these two while loops. So either our starting step size is too big and we need to make it smaller, or our starting step size was too small and we need to make it bigger. Okay. All right. And so at this point, phase one is complete. And so now we are going to evaluate our, our X min as well as our the value of our objective function at the minimum. Okay, so we compute X min here. That's the same formula that we used in class. And this is just evaluating the objective function at that X value. Okay. Okay, from there we form a surrogate function. And then we check and see whether this surrogate function is a good approximation. Okay. So this while loop here will start phase two. But that's the idea with phase one. So phase one, we start with an initial step size. We have these two while loops to adjust the value based on, making sure that we are in the right ballpark. And then we compute our initial surrogate function. Okay. All right. Any questions on how phase one is implemented? Okay. Good. Okay. Phase two. So phase two, this part is a little bit more complicated. Okay. So if you notice, we have another while loop here. So whenever you have an algorithm that's going to repeat until a certain condition is met, the best way to do that is through a while loop. Okay. So the part that I've circled there, if you look back in your notes, at the end of each iteration on phase two, there's a certain condition that we have to check to make sure that, we are, whether we're converged or not. Okay. And basically what we're checking here is we're checking the value of the surrogate function at our current X min, and we're checking the value of our original function at that same value. And if these two are essentially the same, then, then we can stop the algorithm. Okay. But, if the error or if the difference between our surrogate function and our original function at that minimum is very large, then we launch into phase two. Okay. Okay. All right, so the next part here, so now that we've kind of reached this part here, we've kind of decided already that we need to refine our surrogate. And so if you remember in phase two, there are kind of those 4 rules that we need to choose, okay? And that's depending on the value of X min relative to the step size, and depending on the value of the objective function at the minimum relative to FB, okay? And then based on those 4 conditions, we're going to rearrange, the different F values with the different X values, okay? So to kind of illustrate those 4 different conditions, you can see here I've used an if, else if, else if, else statement. Okay. All right. So this is kind of one of the best, probably the best kind of example of using an if statement, is because you have these 4 conditions, and depending on which condition that you're in, you're going to do something different with the objective functions and rearranging the x values. Okay. And so if you read through the logic here, you'll see that this matches up exactly kind of what we have in class. Right? So this part of the code here, honestly, for me, I think is probably the best part to kind of analyze when you're kind of reading through this code. Because this is a great example of, taking our algorithm, which we kind of described in words, the last two lectures, and seeing how that logic is implemented in the code, right? And a lot of optimization, at least when you're implementing it, is exactly like that, where you're taking kind of a logical procedure, a logical algorithm, and you're saying, all right, how do I put this in a form that the computer can understand, right? So this if statement here is kind of a great example of that. So, definitely go through this, look back in your notes, look at the how phase 2 starts and see how it correlates with this if statement. Okay. Okay. So once we've chosen how to refine our surrogate, we need to recompute the surrogate value itself, okay, or surrogate function. So that means recomputing the values for A, B, and C, right? And if you remember, the formulas for A, B, and C are different in phase 2, and so we want to make sure we use those same formulas here. So these formulas, they look pretty intimidating, but you'll see that they match up kind of exactly what we have in notes. Okay. From there, once we have a new surrogate function here, we compute a new x minimum. We evaluate the objective function at that location, and then we evaluate our surrogate model at that location as well. Okay. All right, and then at this stage, once we've kind of recomputed our surrogate, we then come back up to the top of the loop, and then we check again. So, now that we've recomputed our surrogate, we're going to check and see if we've converged. If we haven't converged, then we just kind of repeat the entire process, and we just keep repeating this until we reach our optimum value. Okay. And then everything down here, all this is just for plotting. So, technically these aren't necessary, but I included it there just so that you can kind of see, just so you can kind of see the function. Okay. Okay. Any questions on this before I run the code? Okay. All right. So let me go ahead and run the code. Okay. And it should be producing a plot. There it is. Okay, so according to this code right here, the code was able to find that there is a minimum value. So the optimum x value is 1.998, so pretty much right on the dot at 2, and it has a function value of minus 43 about, okay? And it achieved this in 7 iterations, right? And so if you look at the graph here, okay? And so in blue there, that is our surrogate function. And so you can see that it converges right on the same minimum right there at right about 2. And then in the red there, that is our original objective function. Okay. So you can see that our surrogate function isn't perfect. So, you can see that the red function there does some pretty weird stuff. And so, it's kind of impossible to make a quadratic function follow that exactly. But at least in the neighborhood of the minimum, we are pretty dang close. Okay. All right. Any questions on that? Okay. All right. And so with that, you should be good to go for the homework. Remember, part of homework 4 is to implement a MATLAB code that that implements the interpolation method. So use this example code. So this is 1D NLP example 3, and just modify it according to the homework problem. Okay. So don't start from scratch, but use this. But again, as long as if you are using this, then make sure you kind of read the code to kind of really understand it. Okay. If you really want to challenge yourself, you can definitely try implementing these from scratch. But just be aware that it is a lot of work. Okay. Okay. All right. So let me go ahead and bring back the pad here. Okay. All right, and so that closes the chapter on interpolation methods. So interpolation methods, that's probably the algorithm that we spent the most time on, so far. It's also the most complex by far. So, definitely a really good one to know. So if you can really understand the interpolation methods algorithm, you're going to be in great shape going forward. Okay. The Newton-Raphson method, isn't quite as complex as interpolation methods, but Starting on Thursday, we're going to start working on multi-dimensional nonlinear programming. So those methods tend to be more complicated than these. So you want to make sure you're kind of ready before Thursday, and when we start multivariable stuff. Okay. All right, but before we get there, there's one more method that we have to go through, and that is called direct root methods. Okay. Okay, so direct root methods, like I mentioned earlier today, is not an algorithm that's unique to optimization. It just applies well to optimization. But the idea with direct root methods is that these are numerical techniques for finding the root of a function. Okay. So finding roots of a function is something that is just really useful just in math in general. And so a lot of mathematical theory over the years has been developed, with using the root as a very common technique. Okay. And so the root of a function is that if you have a function, f of x, okay, when we say that we want to find the roots, what we do is we set this function equal to 0. Okay. And then we find out, what values of x in this function cause this function to go to 0. Okay. So probably, what you're used to in probably in your previous classes, your algebra classes is, you have quadratic functions. So there's all different kinds of methods to find the roots of a quadratic function. But, of course, there's way more than just quadratic functions out there in the world. Cubic functions, fourth order functions, sinusoid functions. So, not irrational functions. So, finding roots of non-quadratic functions is usually something that's not really discussed a lot in math classes. Because honestly, it's really hard, right? So if you have some very complicated function, finding the roots of that function can be quite okay. So the idea with direct root methods is to write a numerical scheme to do this for us. Okay. So remember, computers offer us a way to do computations really, very quickly. We just have to give it the right algorithm. Okay. And direct root methods are just exactly like this. Okay. Okay. So how is this useful in optimization, right? Because in optimization, we're not specifically looking for locations where our objective function is 0, right? We want to minimize or maximize our objective function. So the way that we use direct root methods in optimization is we use them to find the roots of not the objective function, but we use them to find the roots of the objective function derivative. Okay. Okay. Which is kind of exactly what we did in our classical methods, right? So in classical methods, we took our objective function, we took the derivative, set it equal to 0, and then by the math of magic, we found the locations of x for that curve. Okay. So for direct root methods, we're going to do that kind of, exactly, but we're using a numerical scheme instead of, our algebra skills. we're going to set df dx equal to 0, okay, at some values of x, and we're going to use direct root methods to find these values of x. Okay. And then just by our theory of, from classical optimization, wherever the derivative is equal to 0, we know that's probably going to be at least a local minimum or a local maxima. At worst, it's going to be, probably a saddle point. Okay. Okay, so direct root methods, kind of take us back to our classical methods. It's just the way that we find the roots is going to be slightly different. Okay. All right. But that's the basic idea for direct root methods, is to, there's all these classes of numerical schemes to find roots of functions, and in optimization, we're going to use them to find the roots of the derivative. All right, any questions on this? Okay, so the method that we are going to go over, we're only going to go over one. We're going to go over one method and kind of a twist on that method, is the very famous Newton-Raphson method. Okay. Sometimes, a lot of times you'll just hear this referred to as the Newton method. But Newton actually developed this with the help of his student, Raphson. And so that's why, I try to give credit where credit's due. So, I call it the Newton-Raphson method. Okay. Newton is known for so many other things anyway. So he should give credit to some of his students sometimes. Okay. All right. So I'm not going to go through the details of the method itself, or at least how it is derived. It's a fairly short derivation, but it does involve Taylor series. I'm just going to give you kind of the upshot. Okay. Okay. So the Newton-Raphson method, it is an iterative method. So that means it's something that we need to repeat over and over again. So it's not something that we can get in just one shot. And so the way that the Newton-Raphson method is usually defined is through what's called a recurrence relation. And so if you've never used a recurrence relation before, if you've never heard that before, it's basically the way it works is that you have a current guess, okay, and the recurrence relation will tell you how to get the next guess, which should be an improvement over your current guess. Okay, so given a current guess for the root okay, and so the current guess for the root of the function, we'll call it x sub I. Okay. Okay. The recurrence relation will tell us how to obtain the next best guess, which we're going to call x of I plus 1. So this formula for xi plus 1 is given by this recurrence relation. Okay. So this is a very famous Newton-Raphson formula. Very simple. So xi plus 1 is equal to xi. Okay. So to find the next guess for the root of the function, you're going to start with your current guess, and then you're going to modify it according to the function derivatives. So we have minus f prime evaluated at xi, okay, divided by f double prime evaluated at the same location xi. Okay, and that's it. So that's the very famous Newton-Raphson formula. Okay, at least in one. There is a multi-dimensional version of this. We may have time to go over it. Um, we'll see. It depends on how quickly we can get through the multivariable stuff. Okay. Okay. So that's it. So that's the algorithm. So or that's the main part of the algorithm. So actually the full text of the algorithm is fairly short, right? So what's nice about the Newton-Raphson method is that you don't have to estimate a step size. And so if you think back to our dichotomous search, we think back to our interpolation methods, a big part of those methods was that we had to estimate an initial step size. This one we don't have to, it's already kind of given to us by this formula. Okay. So step one of the algorithm is to start. We're going to start with an initial guess for the optimum of our objective function. Okay. So your initial guess here, it doesn't have to be, you don't have to be too careful with the initial guess, but it should hopefully be in the right ballpark, right? So you can test this, and so you can test and see what happens when you start with an initial guess of like 1 billion, and see kind of how that goes. I actually don't know how it's going to go for the homework, but that's something you can do. Okay. Okay. Next thing you're going to do is you're going to evaluate the objective function derivative, so both the first derivative and the second derivative at that initial guess. Okay. Right. So you may be looking at step two and you may be thinking, wait a minute, I thought we were doing methods here where we don't have f prime. And you're saying that for this method, we actually need both f prime and f double prime. So this step here seems to break all of our rules for nonlinear programming. So, in order to do step two, we need to have explicit expressions for f prime of x and f double prime of x. Right? Which seems to kind of defeat the whole purpose of nonlinear programming, right? And so nonlinear programming, we're supposed to only be able to do function evaluations. And you're right. And so that's why, for this, probably the main one that you're going to be using is not the Newton-Raphson method, but the quasi-Newton-Raphson method. So we'll go over that one after. But the quasi-Newton-Raphson method, has a way of approximating these things based on just the function evaluations. Okay. So just be a little patient. I know this seems a bit complicated, or this seems to be kind of go against everything that we kind of stand for here at NLP, but just be a bit patient. Okay. But even so, this method still is very convenient, because there will be situations where maybe you have your objective function explicitly and you can take its derivative, but maybe that objective function is in a certain form that's really difficult to find the roots of the derivative. Okay, so even though you have it, it's really hard for you to find the roots in kind of a traditional way. Okay. So think of, I think we did one homework problem like this in homework, is either homework 2 or homework 3, where I gave you kind of a function and you took the derivative and you ended up with some fourth order function where it's hard to find the roots of that function. So, Newton-Raphson can kind of help you out in those cases. Okay. Okay. Step 3 of the algorithm. Step 3 is to use the recurrence relation above to compute your next guess for the optimum. find the next guess. Sorry. All right, so you're just going to take the ratio of the first derivative over the second derivative at that location and subtract it from your initial guess. Okay. All right, step 4, we're going to check for convergence. Okay. So how do we know when our Newton-Raphson method is converged? Well, how do we find out when our optimum was reached in classical methods? In classical methods, we reached the optimum when the first derivative was equal to 0. Okay. So if f prime of xi is equal to 0, or if you're implementing a code, it's very hard for a method like this to reach exactly 0. So oftentimes you just have to tell it, how you just have to get very close to 0. Okay. Okay, and so if that's the case, then we found the optimum and we can exit. Okay, if not, we're just going to repeat the whole process. And so if not, we're just going to return to step 2. All right, so that's the algorithm. So quite a bit shorter than our interpolation methods. And that's kind of by design. Okay. All right, any questions on this before we hop into an example? Okay. All right, so let's do an example so you can kind of see this in action. Okay, so let's consider this objective function. So I'm going to give you kind of a nasty one here. So let's say f of x is equal to 0.65 minus 0.75 all over 1 plus x squared minus 0.65x multiplied by tan inverse of 1 over x. Okay. All right, so that is one gnarly function there. So this is a function that we actually can take the derivatives of this, but finding the roots of that derivative are going to be very, very challenging. So this is kind of the perfect function that we can use to apply our Newton-Raphson. Okay. All right. So what we want to do is let's use Newton-Raphson. I'll give you the initial guess. So we're going to start with initial guess of 0.1. Okay. And so we want to find the optimum of this function within a tolerance of 0.01. Or let me see, find optimum up to where f prime of x is less than or equal to 0.01. Okay, so that's our tolerance. And so as long as our derivative, or at least I should say the absolute value of the derivative, as long as the absolute value of the derivative is less than 0.01, then we're going to say that we're close enough. Okay. All right. Any questions on just the setup for the problem? All right, so before we actually start iterating here, let's first compute the explicit expressions for the first derivative and the second derivative. Okay. Okay. So you can see here there is quite a lot of chain rule, product rule, quotient rule here going on here. So there's a lot of shenanigans going on with this. I have no idea what I was thinking with this example. So okay.
Won't show off.
I don't want to anymore because I don't want to do this work anymore. Okay, all right. So thankfully I have the solutions here already, and I really want to get the quasi Newton-Raphson because you're not going to be using regular Newton-Raphson all that often, but I just want to kind of show you the how it's done. So let me say after some work, okay, some in quotes there, okay. All right, so after some work, we obtain our derivative here. So I've already tested you guys on taking derivatives analytically. That was the first midterm. So we're not going to do that again. This next part of the class is all about algorithms and implementing them in MATLAB. Okay, so this derivative here, it is 1.5 x divided by quantity 1 plus x squared quantity squared, okay, minus 0.65 and inverse of 1 over x plus 0.65 x all over 1 plus x squared. Okay. Of course, the key tenet to this is the fact that derivative of tan inverse is 1 over x squared. Okay. Okay. So that is the first derivative. And so again, technically you can solve this problem using the classical methods, but if you were to set this expression here equal to 0, good luck trying to find the value of x that make that 0. Not the easiest thing to do. Okay. All right, so the second derivative, let's see, second derivative here, this one was a bit more work just because there's a bit more chain rule. And so this ends up being 1.3 all over 1.1 plus x squared plus 1.5 minus 1.3 x squared all over 1 plus x squared quantity squared minus 6x squared divided by 1 plus x squared cubed. Okay. The work for this is all in the notes. So I actually did do this, right? So, but you can check the notes for the details. Okay. Again, the details for how to take derivatives, not as important here. We're going to focus our efforts on the quasi-Newton. Before we get to quasi-Newton-Raphson, we have to look at regular Newton. Okay. All right, so now that we have expressions for the first and second derivatives, we can go ahead and start launching into our Newton-Raphson iterations. Okay. So since this is an iterative method, we'll go ahead and label these iteration 1, 2, 3, just so we can keep track of how many times we've iterated. Okay. Okay, so we'll start iteration 1. Okay, so on this first iteration, our current guess for the optimum is our initial guess. Okay, so we have x naught is equal to 0.1 Okay, remember this was our initial guess. Okay. All right, so to get our next guess for the optimum, we're going to evaluate our first and second derivatives at this location. Okay. So we're going to evaluate f prime of 0.1. Okay, so we're going to take 0.1 and plug it into this expression here for f prime. So we have 1.5 times 0.1 divided by 1 plus 0.1 squared, 1 squared, and so on and so forth. Okay, and so plugging that into a calculator or MATLAB, we get minus 0.745. Okay. We do the same thing for the second derivative. We plug that in, we get 2.687. Okay. All right. So now that we have all three of these things, we can compute our next guess. And so we're going to plug this into our recurrence relation. Okay. So for our recurrence relation, we have x1 is equal to x0 minus f prime of x0 divided by f double prime of x0. Okay. If we go and plug in for this, so we have 0.1 minus 0.745 divided by 2.687. Okay. And so, first thing you see here is that, if we look at the value for f prime at 0.1, we can see that it's non-zero, right? So we know that we're not converged right now. And so we get this next guess. This next guess is x1 is equal to 0.377. Okay. So we moved quite a bit. So we went from 0.1 up to 0.377. Okay. Now we're going to check for convergence. So since f prime of x naught was greater than or equal to 0.01, we are not converged yet. Okay. All right, so then we launch into the second iteration. Iteration 2, we're going to start with the guess that we ended with on the last iteration. Okay, so we're going to start with an x value of 0.377. Okay. Just like before, we're going to evaluate our first derivative at 0.377. We evaluate that, we get negative 0.138. Evaluate our second derivative at that same point. What we get is 1.573. Okay. So you can see here that we are not quite there yet. So we are still not converged at this step. Okay. All right. And that's based on our value for f prime. And so from here, we're going to use our recurrence relation. We're going to get x2. So x2 in this case is 0.377 minus negative 0.138 divided by 1.573. That's going to give us our next guess, which is 0.465. Okay. So we're not converged quite yet, and so we're going to go launch into iteration 3. Okay. So since absolute value f prime of x1.
Does it mean something that it got bigger?
That the value for x?
Yeah, because x1 was 0.377 and x2 is 0.465.
Yeah.
So you're almost closer to your first initial guess.
Well, this one we start with an initial guess of 0.1. So it is significant that we are moving forward. So generally for Newton-Raphson, once you kind of start moving in one direction, you keep moving in that direction. Sometimes when you're really close, you may oscillate between, going up and going down, but generally it always goes in one direction. That's a good observation.
I think I was also confused though that F prime of X is getting smaller.
Oh, yeah.
Closer to zero.
Yeah, the F prime of X should be getting closer to zero too, because if that's getting closer to zero, that means we're getting close to convergence as well too. Yeah, yeah, good observations.
So if you're getting further away from 0.01, you have to go the other direction.
Well, hopefully that's not the case. So this method here is designed to always make sure that you're going towards the root. And so if you're getting further away from the root, then maybe something has gone wrong, or maybe the function itself isn't appropriate use for Newton-Raphson. There are some limitations. Newton-Raphson only works when you have a continuous function. If you have a discontinuous function, then Newton-Raphson is not going to work on those cases.
But that's because you told us where to start from.
That's true. Yeah. So if you were to start, so if you wanted to, you can test and see if you started this function like 1 billion, then yeah, it might still reach. So Newton-Raphson is actually a very stable method. And so as long as you can get the first and second derivatives, it should converge. It may take you, probably 5,000 iterations to go from 1 billion down to, where it looks like we're trending towards 0.5.
Are we going to be using MATLAB for this as well?
Yes, yeah. For the most part, you're going to be using MATLAB. For the homework, I have you working some of these out by hand, just so you can kind of, understand every step of the algorithm. But for the most part, these are meant to be MATLAB outcomes. The ones I give you in the homeworks are, I tailored them so that you don't need that many. Okay, so let's do one more. Oops. Okay, so iteration 3. So this time our starting point x2 is 0.465. Once again, we're going to compute our derivatives here. So you have f prime of 0.465. You can see that is minus 0.0179. So we're very close here. And so f double prime at 0.465 in this case is 1.171. Okay. And so we're going to compute x3. X3 we're going to compute is 0.465 minus 0.0179 over 1.171. Okay. And so we do that arithmetic. What we get is 0.4805. Okay. Okay. So technically, we knew already that we weren't converged at 0.465, but let's check the conversion at 0.4805. Okay, so what we're going to do is we're going to evaluate f prime at 0.4805. Okay. And so we plug it in, what we get is minus 0.0005. All right, so when x is equal to 0.4805, that means, what we can see here that our slope is pretty much zero, or very, very close to zero. And so, you can iterate one more time if you really want. But it's not really going to lead to all that much improvement. And so from here, we can see that our method is converged. Okay. And so the optimum in this case is x is equal to 0.4805. One other neat thing that you can do is that because you're computing the second derivatives anyway, you can check to see whether you have a max or a min, okay? And since our second derivative, you can see here, has been consistently positive, this tells us that our x value here is a min, okay? Usually not that important, usually it's kind of clear, but just a little bit extra trivia to kind of tie in what we talked about in the first half of class. All right, any questions on this example here? Okay. All right, so that's good. So Newton-Raphson, again, very, very famous formula, very, very, very famous algorithm used for lots of different things. Okay. But how useful is this really for optimization? Because in order for us to use this method, we had to manually compute the derivatives of our objective function. Okay. Right, which we usually don't want to do, right? So usually we just want to work on just the objective function itself and taking its evaluations. Okay? So then, it kind of begs the question of, can we modify this method? Okay. Can we modify this method so that it only requires us to use function evaluations? In other words, so that we don't have to compute the derivatives by hand. Okay. Because if we can do that, then this method will work, basically for any function, and we don't have to worry about taking derivatives of kind of monstrous functions. Okay. Wouldn't it be funny if I said this and said the answer is no, and then we just kind of move on from here? Of course, it's possible. Otherwise, I wouldn't bring it up, right? And so this has led to the creation of what we call kind of a quasi-Newton-Raphson method, where it's not exactly Newton-Raphson, but we modify it in a way where we don't have to take derivatives by it. Okay. So basically, the idea with quasi-Newton-Raphson is that instead of computing the derivatives exactly, right? One thing we noticed from the Newton-Raphson method is that when we use the derivatives, right, when we plug into the recurrence relation, we only need the derivatives evaluated at a certain location, right? So in the previous example, we computed the derivatives explicitly, mostly just because we didn't really know any better, right? And so technically with these expressions, we can evaluate the derivative at any location x, right? We just have to plug in for it. But this is a little bit overkill for our use, okay? So in the recurrence relation, we only have to evaluate the derivatives at specific locations. Okay. So let me go ahead and I'll go ahead and rewrite the recurrence relation just so I can just so you kind of see what I mean. Okay. And so if you look at the structure, if you look at how this recurrence relation is structured, right, we have our two derivatives there. We have f prime of xi and f double prime of xi, okay? But we're only evaluating these derivatives at a single location xi, okay? And so that kind of gets, people thinking that, instead of computing our derivatives exactly, what if we approximate our derivatives using something a little bit clever using a technique known as finite differences. So I know some people have experience with finite differences. I think if you took heat transfer with Dr. Banks last spring, probably he might have introduced this. But if you've never seen finite differences, the basic idea with finite differences is to approximate derivatives using kind of the base definition of a derivative, right? Okay. So I'll just kind of give a very kind of quick explanation here. For this algorithm, you're mostly just going to need the formulas, but it helps to kind of know where the formulas come from. Okay. All right, so let's say we have a function. Okay, so let's say our function kind of looks like that. And so let's say that we want to compute the derivative of the function at a particular location, right? So let's say that, I've chosen this location right here. Okay. And let's say that we want to compute the derivative of the function here. Okay. Okay. So what is the derivative of the function? The derivative of this function visually is nothing more than just the slope of the line, right? So we can compute the slope. So one way is we can just take the function f if we have its explicit expression, just take the derivative of it normally. But if we have this graph here, there's a way that we can compute the derivative without actually invoking the derivative operation. Okay. Because what if I do this? And so let's say that we want to take the derivative there, but in the immediate vicinity, and I'm going to go ahead and zoom in just so you can see. Okay. So within this immediate vicinity, so let's say that we go, maybe delta x in this direction, and maybe delta x in this direction. Okay. So delta x is just some small value of x. Okay. And then I evaluate the function at one location that is a little bit upstream, so it's a little bit to the left, and then one location a little bit downstream. Okay. And so if we call this location here, so we'll call this f of x I minus delta x, and then this location here is f of xi plus delta x. Okay. Okay, so basically we are evaluating our function a little bit to the left, a little bit to the right of our chosen point. Okay. Okay. We can use those points to approximate our slope, right? Because if we do, so let's say that we do this formula here. So let's say that we do f, we take the location to the right, f of xi minus delta x, or plus delta x, excuse me. Then we do minus f of xi minus delta x, okay? And then let's say we divide that by the distance in between those 2 points. And so if we went delta x to the left and then delta x to the right, then the total distance in between those 2 points is 2 delta x. Okay. This formula here should look pretty familiar. So, if you think all the way back to Math 150A when you're first learning calculus, right? And you're first learning the definition of a derivative, right? And so if you think back, the definition of a derivative is nothing more than just, the limit as dx approaches 0 of f of x plus dx minus f of x minus dx all over dx, right? So this formula that we kind of concocted here looks very similar to this, right? And, you know, there's another way that you can view this too, which is kind of our traditional way of thinking of slope, which is simply rise over run, where the numerator here is the rise or how much the function is changing in value. And on the denominator is a run, which is the horizontal distance that we travel from there, okay? And so what we can say is that this numerical expression up here, okay, this numerical expression is equal to f prime of xi. And in fact, that formula right there is exactly the what we call the central difference approximation of the derivative at a location xi. Okay. So this right here is the finite difference. Okay. That's the finite difference approximation of f prime of xi. Okay. All right. Any questions on how we obtain this this finite difference formula here? Okay. All right, so what do you notice about that formula, right? So this formula here on the left-hand side, this formula here only relies on the function evaluations, right? So there's no mention of the exact derivative here. So that's great. So that means, you know, if we replace in our Newton-Raphson iterations here, okay, if we replace this f prime with its finite difference approximation, then we can get around the requirement of needing the function derivative, okay? And in fact, you know, there's also a finite difference approximation for the second order derivative as well. I'm not going to illustrate this just because this one takes a bit more time, but, you know, there is an approximation for this. For the finite difference So the finite difference approximation of f double prime of xi is f double prime of xi is equal to f of xi plus delta x minus 2 f of xi plus f of xi minus delta x all over delta x squared. Where again, you know, this expression here, this finite difference approximation only depends on the function evaluations. Okay. Granted, you know, this does increase the number of function evaluations that we have to do, because not only do we have to evaluate the function at our chosen location xi, but we also have to evaluate the function to the left and a little bit to the right. Okay. This also requires us to choose a step size once again. So, you know, we can't really escape the step size here, although the step size here has a little bit of different interpretation. So we need to choose this value. Okay. Usually you're going to choose it to be something fairly small, especially just because, you know, you're going to be using a computer to be computing these things anyway. Okay. And generally, the smaller you make delta x, the more accurate your finite difference approximations are. Okay. But if you can imagine, and we'll do this next time, where if you take your Newton-Raphson iterations here and you replace the two derivative terms with their finite difference approximations, then now your recurrence relationship does not require the derivatives explicitly, but now instead relies just on the function evaluations. And once again, we have an algorithm that kind of fits our criteria for nonlinear programming alpha. Okay. All right, any questions on this before we wrap it up for today? Okay, all right, so next class, I'll go ahead and show you the full expression here. So I'll give you, I won't leave the plugging in to just you. So we'll go ahead and plug that in. I'll give you the final relationship for quasi-Newton-Raphson, and we'll go over one last MATLAB code to see how this is implemented before we get into the multi-dimensional stuff. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Thursday.
You did. We used to do the color. Well, I don't know if the color was. Sure. No, I think your color. Always been the same jacket. I was waiting for a response back.
Okay.
We're doing okay.
Check with you. Sounds good. It's not a huge, we're kind of like, it'd be nice to.
No, but we've been, modifying a lot of our SolidWorks before they like, have revisions that want to.
Oh, yeah. Yeah, sounds good.
Well, then theoretically.
Okay, next line's up.
Okay. Yeah, thanks for that.
I'll create another one or make another batch.